Hello, my name is Indrajit Kaur, and today I will be presenting the paper Vibe Video Inference for Human Body Pose and Shape Estimation. And it is authored by Muhammad Nikos and Michael J. Black at the Max Planck Institute in 2020. This paper mainly focuses on advancing how we estimate 3D human body pose and shape from regular videos. Let's move to the next slide, which is motivation. Understanding human motion is important for AR, VR, healthcare, sports, robotics, and more. Most existing methods work on single image, but when applied to video, results are often jittery or unnatural. The key problem is that there's very little 3D annotated video data in real world settings. Vibe tries to solve this by learning motion realism without requiring such data. Moving to the next slide, which is problem definition. The goal is estimate accurate natural 3D pose and body shape from monocular video. Challenges include no reliable 3D label for in the wild video. Motions must be continuous and realistic. Prior methods produce jittery or implausible results, so the task is not just predicting poses per frame but generating smooth sequences as well. Moving to the next slide, which is dataset and features. To train Vibe, the authors combined several datasets. First one is AMAS, a large motion capture dataset for motion realism. 2D datasets like pen action, post track, insta variety for 2D key points. 3D benchmarks like Human 3.6M, 3D PW, which is 3D poses in the wild, and Max Planck Institute for Informatics. 3D human pose dataset for evolution. They use the SMPL body model to represent both pose and shape consistently. Moving to the next slide, which is slide 5, and which is about model and approach. Vibe has three main parts. First one is CNN, encoder extracts frame features. Second one is temporal encoder, which is GRU, captures motion across frames. Third one is motion discriminator, which is trained with a mass and distinguishes real from fake motions, encouraging realistic sequences. A self attention mechanism helps the system focus on the most informative frames, and together this produces smooth, plausible 3D body motion from videos. Moving to the next slide, why this approach? The design tackles key challenges. Adversarial training allows learning motion realism without labeled 3D video data. Next is temporal modeling ensures consistency across frames. Third one is attention emphasizes critical frames like fast transitions, and the combination directly addresses the weaknesses of earlier methods. Next is evolution matrices. To evaluate the model, the authors used several metrics. First one is mean per joint position error, the average distance between predicted and ground truth joints. Next one is MPJPE, which is after grid alignment and which removes global translation and rotation errors. Next one is per vertex error, which compares the predicted body mesh vertices with ground truth. Moving to the next, which is percentage of correct key points. That helps to measure how many predicted joints are within a threshold of the ground truth. The last one is acceleration error, which helps to measure how smooth the predicted motions are by comparing accelerations with the ground truth. And these matrices together cover both accuracy and realism, which is critical for human motion estimations. And the next slide is results and outcomes. Vibe achieved state of the art performance on benchmarks like 3D poses in the wild and 3D human pose dataset. It outperformed single frame models and even prior video methods like human mesh recovery, producing both smoother and more accurate results. Ablation studies showed the motion discriminator and the attention mechanism were critical to its success. Some key takeaways are motion modeling is crucial for 3D pose estimation. Next one is adversarial training with motion priors is powerful. Next one is video models consistently beat single frame ones. Attention helps capture important motion cues. Next is limitations. Vibe also has some limitations as a mask doesn't cover all real world motions. There's a trade off between accuracy and smoothness. Training is computationally expensive and not real time yet. So the conclusion is Vibe advances video based 3D human pose and shape estimation by combining temporal modeling, adversarial learning, and attention. It bridges the gap between motion, capture the data, and real world videos, achieving state of the art results. So, future directions include transformers, optical flow, and handling multiple people at once. So, thank you, and here are some references uh, for the information regarding why. Thank you for watching my video.